We're going to look at heat of formation and how to find the heat of a reaction. This delta H here stands for the heat of reaction. And one way of doing this is by looking at the bonds breaking. So here we have a reaction coordinate with potential energy. The reactants have to break bonds, and then they get into their transition state, and then to make new bonds. And this here is an example of an exothermic reaction, and the delta H in this case would be negative. Now you could also apply this for an endothermic reaction, obviously. Now using the energy diagram, this allows us to look specifically at the amount of energy needed for this process. Now a simple process, some way of simplifying some of this information is when you have elements coming together like hydrogen and oxygen, these produce water. And the production of water, again, this is a combustion reaction of hydrogen with oxygen. You got 2 moles of hydrogen to make 2 moles of water. And the heat for this reaction is also called the heat of formation because you're forming water. So this is called the delta H sub F, heat of formation. And this has a value of negative 286 kilojoules per mole. Whenever you form a compound from its individual elements, you can also simplify this reaction here so that you have H2 plus a half of an O2 making a water. And the delta H for this reaction is still negative 286 kilojoules per mole. And because it's a mole of the water you're making here, both of these reactions are showing the same information. So sometimes chemists will use this reaction because it's just a little easier to work with, even though it has the half and it's not a full complete number there. Now, when you form a compound here, you're making bonds. So making bonds is like forming a compound. So breaking bonds would be like the opposite of forming. So when we look at our delta H equation, it's the energy to break bonds minus the energy that is used to make these bonds. So the energy here, when you're looking at bond energies, this is an equation, a way of showing those bond energies. When you're looking at heat of formation data, when you have heat of formation data, this data is usually found experimentally, and you can look this up on a table. It's called a heat of formation table, standard heat of formation table. So to look at an example of a problem like this in our lab manual, if we turn to page F185, the first reaction here is magnesium oxide number 1. So magnesium oxide solid plus H2O liquid makes magnesium hydroxide solid. Now in this reaction here, you're going to have new compounds formed and other compounds broken down. So to calculate the total delta H for this reaction, what we do is we consider the sum of all the bonds formed. So we take the sum of the heat of formation data of all the products, and we subtract, because the reactants are going through the opposite process, they're breaking down, not forming, so we subtract the sum of the heat of formation of the reactants. So this process here is showing the amount of energy for the entire reaction. So to do this for this example equation, what we can do is we can look up the values for each of these here. So the first product we have is magnesium hydroxide, and on the back of F185 we look this up, and this value has negative 925.0, that's kilojoules per mole. And then we look at our reactants, MgO has a negative 602 kilojoules per mole, and our water has a value of liquid water negative 286 kilojoules per mole. So what we need to do is we need to take the value of the products, so the delta H, the first product is the magnesium hydroxide, there's 1 mole of it, times the negative 925 kilojoules per mole. It's the only product we have, so that's the sum. And then we subtract the sum of all the reactants. So the first one, we've got 1 mole of magnesium oxide times negative 602 kilojoules per mole. And then we add to that, we got 1 mole of water times the negative 286 kilojoules per mole. Oh, there we go. So there we go, kilojoules per mole. So now what we need to do is we need to add these two over here up first. And again, using the scientific calculator makes this step a lot easier, plugging it in. But all we do here is we take 1 times 602, and this is going to equal negative 602 kilojoules plus negative 286 kilojoules. And when we add those two together, we get a value of negative 888 kilojoules. This value over here is the negative 925 kilojoules when we multiply out the moles. And now to find the delta H, we just add these two numbers up, so to speak. So we got negative 925 minus negative 888. So negative 925 minus negative 888 gives us a delta H value of negative 37.0 kilojoules. And that is known as the heat of reaction for magnesium oxide plus liquid water making magnesium hydroxide. And that is how to find the energy change for a chemical reaction given the heat of formation data. Let's look at a second example. So if we look at a second example, let's look at example number 6. So on number 6, we have CH4 gas plus 2O2 gas makes CO2 gas plus H2O liquid, and there's 2 of these here. Okay. So we set up our products minus our reactants. So the first product I have is CO2, so I got 1 mole of that. We look up the value of CO2 gas, and it's negative 393.5. Okay, then we add 2 times the liquid water, which is negative 286. That all goes here. And then we subtract the reactant side, which is CH4. CH4 gas is negative 75. And there's 1 mole, so I'm not including that in there. And then 2 moles of the oxygen gas. And you look up oxygen, and it's not there on the table. The reason why is oxygen gas is a element, so its value is 0. So this gives us here a 0 here, negative 75, so that's negative 75.0. Minus that, and then you get 393.5 286 plus 286. And this should give us a value of negative 965.5. And then we're subtracting from that 75, negative 75, sorry. And this gives us a total delta H value of negative 890.5 kilojoules, which is what you expect for methane. 890.5 kilojoules for the reaction, and you got 1 mole here, so its value is 891 kilojoules per mole negative, and this is approximately what we have been working with for our delta H for the combustion of methane. So those are some ways to use Hess's law to determine the heat of a reaction.